relatively easy, right? So let us go through the questions in the quiz. I think I forgot to do this for the first quiz, right? So this is the first question, right? So not x means, all the bits are inverted, right? So it's like the ones complement. So 1000 will be the output, and then plus 1. So 1000 plus 1. So I think everybody would have got this, right? The answer is 9. See, it is because it is not in a signed number. So unfortunately, it will print 9, right? I agree with you that 1001 is the it represents -7 in two's complement. But for that, you have to write it as bit signed 3:0. Okay. Then here, see, that was, I was hoping that you will see this one and correct the answer there. So here, bit signed x and y, both x and y are signed bits. And here we are inverting everything. So that became 1000. Then arithmetic shift right. Okay. So 1000, when you write shift, what do you get? You'll get 1100. Am I right? 1000. When you write shift, arithmetic right shift, that one gets copied. Okay. So 1100, and that is being displayed as a signed number, right? So what is 1100 in signed two's complement? It's -4. Yeah. So this I think many would have got. Okay, this is the correct answer. It looks like it shows the correct answer. It shows the correct answer for some reason. Okay. And then test. I'm sorry. There is a task decrement which takes 2 bits, first time and last time. Okay. And if it is the first time, it will initialize x to 20, and x has been declared as a static integer. Then if it is the last time, it will display, and otherwise it will decrement. Okay. So here we are initially making it 10. That means we are initializing x to 20. Then for t equal to 0 to 10, okay, 0 to 9. That means 10 times we are decrementing. And so when I say 1, it actually decrements, right? So 20 will become 10. Okay, and finally we are displaying. So the answer should be 10, right? So many would have got this correct, right? And module, both of these are available, logic and bit. So I hope you remember the difference. Logic is 4 state. Each bit can take 0, 1, x or z. And initially we have put 10 and 5. Okay. And see, the thing is, there is a little bit of a trick here, right? See, when you say initial begin and give non blocking assignments and immediately display. Okay? See, unfortunately, these are non blocking assignments, meaning that it doesn't wait for this assignment to complete. It will go on and do display. So as a result, the values are actually x. Okay. But because y is a bit, right, it will initialize it to 0, right? So the answer will be, it will actually print x0, and none of them are here. Okay, so the answer here is none of the above. Okay, I hope, is that clear to everybody? Mhm. So hopefully you guys got that right, right? And then here I have given blocking assignment. So it will wait for the assignment to complete, and then it will display. So this one is See, unfortunately, we gave big numbers. So 100 cannot fit in 4 bits, right? So the last 4 bits of 100 and last 4 bits of 25 will be kept. And so I believe 25 is 19 hexadecimal. Okay, so 9 will be printed. And this is 64 in hexadecimal, so 4 will be printed. So the answer is 4, 9. Okay, all right. Then there are 4 values. Which of these are not 4 state? See, integer is 4 state. Logic is 4 state. Wire is 4 state. Short int is not 4 state. So the answer is W0. Push front and push back are defined on which of the following data types? Okay. So again, none of these will be the correct answer. Okay. Dynamic array doesn't have push front, etc. It is in the queue. So the answer is none of them. And there's one more. Int I new 5 means dynamic array, right? And here we are initializing the dynamic array. And A1 refers to this 2. Okay. The indexing begins with 0. And A dot size refers to the number of elements, which is 5 minus 1. So we are referring to 4. That means 5. Okay. So fourth element, which is 5. So 5 plus 2, 7 is the answer. So was it showing like this? It is already showing the correct answer. I hope it was not like that for you when you gave the answer. And then there is a class, right? Class counter, count is a static integer. Then we have a function called new, which initializes the value of the count to whatever is given in the parameter. Then display simply displays it. Increment will increment percentage 10. Okay, so it increment and modulo 10. So here we have initialized the counter to 10. Okay, so this statement initializes the counter to 10, and then C1 dot increment will cause it to go from 10 plus 1 is 11. 11 percentage 10 is 1 again. Okay. Then again another increment will make it 1 plus 1 2. 2 percentage 10 is 2. C1 dot display will display it. So again the answer is being displayed here. Okay. So Vineet, I hope it was not showing all the correct answers for them to pick.
Sir, I posted the quiz onto the
Okay.
canvas separately, sir.
Oh, okay. Because here it looks like some of the answers it was showing everything. Okay. Any questions? All right. Anybody else has any questions? Very good. Any questions from yesterday? I remember in the end we had to hurry a bit, right? The class example, unfortunately, we could not get it working on that Icarus. Anybody tried? Anybody successfully managed to get it to work on Icarus? Even I didn't get a chance, but no, I'm sure there is a way to get it working on Icarus also. Any other doubts? Anything else? So yesterday there was a question towards the end that we were working this example, right? What was that example? Can anybody describe the example? What was the example that we were considering yesterday? Anybody remembers? Yeah, Harish Patil is saying we were considering the calculator. Yeah. So it was a stack-based calculator, right? And we did two implementations. One was the, traditional, hardware kind of an implementation, right? And the other one was more like a class-based, right? And I think one of the questions that came up was, what is the advantage that Verilog or VHDL offers in all this, right? Why can't we do this in C or something like that, right? See, initial algorithm development you can do in C. There is nothing wrong, right? You can do any language C, but often when we implement the hardware, right? See, there may be timing issues, right? There may be sort of software offers a lot more flexibility, right? We can do things like print and things like that, which we really can't do in um, development of hardware, right? So debugging hardware, etc., is often a lot more challenging, right? When we develop software, there is a lot of support for debugging and so on. So that is the reason why we need a language which is somewhat close to hardware, right? Which understands concurrency. See, all the stuff in hardware works concurrently, right? Whereas in software, things go more or less sequentially, right? Of course, there are parallel programs and things like that where things go parallelly, right? And you will realize that those are very hard to debug. Right? If you have ever tried your hand with the parallel programming, you will realize that those are quite challenging, right? So you can, without realizing, you can set up races and things like that, right? So when you develop hardware, there is a possibility of such races and hazards, right? And we have to be careful in our verification, right? So we maybe in our examples we have not yet come across anything which requires that kind of verification, but it is important to have a language which models hardware as closely as possible, right? See, in spite of all this, right, there is still a chance that all the work that we did, verification, etc., it still may be insufficient. You understand? See, we try very hard to model it as closely as possible to hardware, and we try to take all the things into account and so on, but uh, it may not be exactly what the hardware does, right? So there may still be some surprise elements when we do the actual implementation. But we can try to avoid as much of that as possible, right? So that is the purpose of verification, right? We cannot entirely avoid, we cannot entirely verify any of the designs using the method that we are following, that is simulation-based method, right? Simulation cannot prove that something works, right? I think I have mentioned that before also, right? It just shows that one test case worked, right? So don't if you are convinced that you have created every kind of test case, that could be achieved, okay, then maybe you can feel that you have a fair amount of confidence in your design. But till that stage, you should continue to test, continue to verify. Okay, so that is the mm, see, because sometimes we see, okay, students when they present their projects, etc., they would have just done some very basic verification, right? Because I was also a faculty at one point of time, so I have seen these kinds of things. So they come and say that, we have finished our project, etc. And then when you ask them, does it work for some other case, they're not very sure, right? And more often than not, those cases will not work, right? So you have to be very careful, right? The purpose of a class on verification is to alert you guys that there is a huge investment in the implementation. Okay, the chip design is a very expensive process, right? So verification is only one gate, right? Once verification is complete, there is a lot more to be done. All that is very expensive, right? And then there is manufacturing to be done, right? And then after all that, if we find that some cases were never tested, they didn't pass at all, the answers were incorrect and things like that, it's a major setback, right? So that is the reason why there are so many people who are spending time doing verification, right? In fact, I think many times if the hardware is very complicated, the companies may even pay others to break their hardware, meaning their hardware model, for example, right? Both internal and external, right? People internal to the company may be given a challenge to see if they can show that there is a bug or something like that, or if necessary, they will even do this for outsiders to see if they can break the. Okay, so such things are done in order to make sure that it is bulletproof, right? Yeah. All right. Any questions? So you must make this a part of your culture, meaning whatever you do, right? No matter how small your project is, right? Test it thoroughly. Okay, it doesn't make sense to introduce too many features, etc., and have a lot of bugs inside, right? And that inside actually is. Say, I'll give you a, sometimes, what can happen is I'll show you maybe in a diagram, I can
इसमें
explain
टमाटर
this to
रखा है
you.
अपने पास और ना लाया है ना हाँ तो और ही डाल सकती है छोटा ले ले एक बारीक काटना धो के
Poonam Kadam, you need to mute. Dr. Poonam Kadam.
ओ सॉरी सर
No. Okay. See, uh, I have seen at least one, I had been invited to be the external examiner of some particular project. Okay, it was an MTech project, and it was some image processing, something like that, right? And I got to look at the code. Okay, and the student actually presented some, for certain images, right? The output. Okay, this was the sample image one, and this is the output for that image one, and things like that. So he had several cases which he even demonstrated and so on, right? But when I went through the code, I was a little puzzled that some particular procedures that he had defined, right, were never being called. He had a procedure for some image processing and things like that, right? And I tried very hard to search where is this being called. I tried to construct a what is called as a call tree, right? And I was finding that many of these procedures are not called. Then finally I realized that the way he had obtained the output was he had manually done something to get the output. He had maybe an editing software or something like that, and he had got the output manually. Okay, See, that was a, number one, unethical, right? And, if you do such things, you will unnecessarily get into trouble, right? In this case, he just got his degree and went away, right? And we couldn't do anything about it. But see, you cannot survive like that in the industry, right? So this is a something that we should all be very wary of, right? If your hardware is not working, or if your procedures are not doing what they are supposed to do, there is no point in trying to mask it and trying to show some false output and things like that, right? So this is unethical, number one, and it will put the company in great difficulty, right? So it is better to be honest and go and talk to the supervisor and say that this is not working, I need more time or whatever. Okay. So in that particular case, the student had to graduate and go. So he didn't want to possibly reveal that there was a problem. Otherwise, maybe IIT would have asked him to stay for another semester and complete, right? Which possibly he did not want, right? But he, in my opinion, what he did was entirely wrong. So you should, unethical practices, should be completely avoided. Okay. So this is a sort of part of verification also, right? I mean, um, there are a lot of ethical questions that also come up in verification, right? And you have to make sure that above all, it is important to be ethical, right? So please make that a point. Don't try to brush things under the carpet and keep quiet, right? Even you will be leaving the company, it's okay, right? Maybe you have decided to leave the company, etc. But that doesn't mean that you should do something like that, like the way that student did, because sooner or later it will come out, isn't it? The That student got away with the problem because I we had already graded him and all that. It's only as a post facto we figured out that there was a problem, right? So I told the supervisor of that particular student that it is what the student has done is unethical, right? Unfortunately, he had already graduated, so nothing could be done about it, right? But if you do such things when you're in the industry, sooner or later people will come to know, okay? And your career will be affected very badly. So please do not follow such things and pay attention, right? It's okay to have a failure, right? And then take some time and fix things rather than so this is a very important you know life lesson that all of you have to have. Okay. All right. So we have been looking at several aspects of system Verilog, right? Um, so so far we have looked at data types, including classes, and we have seen how to model, right? So let me suggest one more uh, you know area, right? That may be of interest to you, right? So there is a this RSA encryption. Okay. So this thing sort of explains it pretty reasonably well, right? So RSA is a encryption algorithm. Okay, I was interested in this because recently there was a news, right, that some quantum computer has cracked an RSA algorithm or something like that, right? So RSA stands for Rivest, Shamir, and Edelman. These are the scientists, computer scientists who designed this encryption method. Right? I'm sure you have heard about it, right? And in many colleges, they teach it as part of course on maybe computer security or something like that. right? So it is a what is called as a public key encryption, right? So it is a public key encryption method, right? And what happens is each user has a public key and a private key. So if I want to communicate with another user, right, I have to use that user's public key and encrypt the message. And the message is open to everybody. Anybody can copy that message, no bars. Okay. Only thing is that message, in order to decrypt it, you need the user's private. Okay. And if you don't have the private key, it is not easy to decrypt this message, right? So for decryption and encryption, it depends on what is called as primality testing. See, to test whether a number is a prime number or not is not an easy thing to do, right? If I give you a big number, right, and ask you, is it prime or not prime, right? And the numbers I'm talking about are really big. Okay, they may be in some 30 digits or something like that. So a very very large number, and the only way to there is only a brute force way or some heuristic ways possibly, right? But none of them can avoid getting into some sort of a brute force technique at some stage or the other, right? One brute force method is, you try to divide by every number starting from 2. Okay. See, half the numbers can be eliminated because if the number is, the prime numbers will be odd only, right? They cannot be even, right? If it's even, then they are not prime numbers, right? So you may have to start with 3 and then 5, 7, things like that. And finally, you will possibly either find that it is divisible and as a result, it is not prime, right? But it takes a long time, right? So as a result, it is very expensive to try and sort of crack this RSA. Okay. So maybe we should see the Wikipedia entry. So this is the Rivest-Shamir-Edelman algorithm. I think they gave it in 1977 is when they gave it, right? And it is still very popularly used. Okay. So today you can see that now the key size is very large, anyway from 2048 bits to 4096 bits. See, the key is very large, right? So that is how it works, right? They, if they find that somebody has, see, initially I think they were using very small keys, right? But what people started doing was they started using distributed computing, massively distributed computing, to try and crack the key, right? So after that they have had to increase the size of the key, and looks like today it is about 4000 bits or something like that. Okay, so the basic principle is this. Okay, if I have a message M, okay, and so E is the public key and D is the private key. So the basic principle behind RSA is the observation that it is practical to find three very large positive integers E, D, and N, such that all integers, okay, uh, both m to the power E to the power D and M have the same remainder when divided by N. Okay. So that is sort of the idea. Okay. So you are only given E and N. So E and N form the public key, okay, whereas D and N form the private key. Okay. So M is a message. M is a message that you are trying to encrypt. N is a large number that you have chosen. N is a very large number that you have chosen. Okay. And E and D are also two numbers that you will derive. Okay. And out of them, E is made public. Everybody knows, right? But D is private. Okay. So given E and N, finding D is very hard. Okay, because it requires primality testing. So usually this is how it works. Two large numbers are chosen. Okay. Two very large numbers are chosen, P and Q, and P and Q are both secret. Okay, nobody knows how they were chosen. And N is a product of those two prime numbers. So you see, that is called factoring, isn't it? Prime factoring, you may have heard, right? Any number can be written as a product of prime numbers, right? See, for example, 6. It's a product of 2 and 3, and 2 and 3 are both prime. So any number can be factored into a product of primes, and in this case, n is n can be factored by a product of p and q, but this is very large. So finding this factor is very difficult. Okay, so that is the thing. You see, this n is like 4,000 bits or something like. Okay. So taking that number and trying to see whether it can be written as a product of two large prime numbers is that is where it's not easy, right? If you try brute force methods like I was telling you, they will take forever, right? So n is used as the modulus for both the private and the public keys, and so n is released as part of the public key. N is a public knowledge, and they also find E using this method. Okay, so E is an integer in the range 1 to what is called as lambda n, right? That lambda n is nothing but uh, number of uh, the number of numbers which are relatively co-prime to n. So that is known as the some people call it Euler's Torsion function, some people call it as Carmichael's Torsion function, etc. So so you can find E, which is the which is also known as a public part of the public key. E and N are public key, right? And then D is found using this method. Okay, and it's not easy to do this. Okay, it is not easy to find the inverse modular multiplicative inverse of E. Is not easy to find. Okay, when we don't know, how to factorize N. Okay, so that is the basic idea, right? So going back to encryption, maybe there is an example here. Okay, so this example will hopefully help you. So here they have chosen P and Q to be 61 and 53. Okay, they are both prime numbers. And as a result, N is this number, 3,233. Then this torsion function is the number of primes less than 3233. How many primes are there between, how many primes, how many numbers are co-prime to 3233 and which are less than 3233. So that happens to be 780. In fact, it is a multiplication of 60 and 52. Okay, so it is a multiplication of 60 and 52. Okay, so that is what it is, right? Then you have you have to choose a number between 1 and 780 that is co-prime to 780. That means they are relatively prime to one another. Okay, so they have tried to say take 70. Okay, just to illustrate. Okay. Then D is what is called as the modular multiplicative inverse of E modulo lambda n. Okay, let us say this they have worked it out to be 430. Okay? Because you take 17 and multiply it by 413 and do it modulo 780, you will get 1. So 17 multiplied by 413, when you take a remainder by 780, you will get 1. So this is something that they have done it because this is a small number, so it's possible to figure it out. Okay. So now everybody knows n, which is the 3233 and 17. Everybody knows this. Now and this is for any one user. Okay, this is for one of the users. For another user, it may be a different e. Okay, so we will have many e's. So remember that any number can be chosen. So if you have a lot of users, you will have to come up with different values of e for different users. Okay. Now the this is the encryption algorithm. Okay, if m is your message, you have to raise m to the power 17 and take modulo 3233. And this is what the user receives. So CM means the uh, encrypted message. So M is a plain text and C of M is the encrypted text. Okay. Now, if I have received C, which is the encrypted text, only the guy who knows D, that is the user, okay, who is the person who has received the message, only he knows D. So he will take C and raise it to the power D. And it so happens that that will be congruent to m modulo this 3233. So he will get the message back. Okay, so here is an example. So they took m to be 65. Okay. 65 may be some ASCII character. So they took 65 and raised it to the power 17, and then they did m modulo 3233. This is that n value, and they got 2790, and this is what they will transmit. At the receiving end, the user will take 2790 and raise it to the power 413 and do modulo 3233, and he will get back 65, okay, which is the original message. Okay. So you can read a little bit more about it. I mean, I have given a very quick introduction, right? But in order to do this encryption and decryption, right? What is it that is involved? So think about it. So I am given a message. It may be an 8-bit ASCII code or something like that. And I'm given E. And I have to do m to the power E modulo. Okay. So think about it. See, suppose I have suppose E happens to be 5 or something like that. And M is, let us say, 65. So it's not easy to do 65 to the power 5. Okay. Because it requires a lot of multiplications. Okay. And then we have to also do it modulo something. So the good thing about modulo multiplication is you can start by saying 65 times 65. Okay. I don't know what is that value. Can anybody tell me? 65 times 65 is how much? 3000, 4000 something, right? 4225. So 4225 modulo 3233. So what is that value? 4225 minus 3223. Okay, what is that value? Subtract 3233 from 4225. So 5 minus 3 is 2, 12 minus 3 is 9, 11 minus 2 is 9, right? So 992. Now 65 multiplied by 992 is what we have to take. Okay? And this will be another big number. And again, you have to take it to modulo 3233. So we have done 65 square, 65 cubed, right? And 65 again with whatever number we get from here. So the advantage of modular arithmetic is you don't have to first compute 65 to the power 5 and then do modulo, because this will be a very large number, right? So we can keep multiplying one at a time. So we multiply 65 square and then immediately do modulo. Then whatever number we get, 992, we multiply by 65 and then again do modulo. Okay. So at least this way, the number doesn't go beyond this 3233 at any point. Okay. So the number remains in this range. Okay. Otherwise, we don't know how to do it, right? It's very difficult to sort of estimate how big a number we want and things like that. So this is called modular exponentiation. Okay. Modular exponentiation. This is modular multiplication. We just we already know how to multiply numbers. Okay, but this is not just ordinary multiplication. After multiplying, we should take modulo a given number. So that is one problem, and then the other problem is to find modular exponentiation. So people have, this is not an easy problem. Okay, this modular exponentiation is people have thought about it, and you will find out there is a lot of work on this, right? And see here, he has explained what it is. Okay, so suppose I want 5 to the power 3 modulo 13. This is a smaller example. So first you do 5 square and then do modulo 13. Okay. And then continue like that, and finally you will get c equal to 8. So maybe we can do this. This is a reasonably small number. So 5 cube modulo 13. Let us do this. 5 cube. So we have 5 cube mod 13. So we can start with 1 and multiply it with 5 and do mod 13. That is 5 only. Then 5 multiplied by 5, that is 25 mod 13. That is 12. Right? Then 25 times 5, that is 125. Okay? So 125 mod 13 is how much? That is divide 125 by 13 and find the remainder. What is that number? 13, how many times? 13 times 7. Okay, the remainder is 8. Okay, so the remainder is 8. That is what one of the students told me. So that is what they are writing here. That is what they have written here. Okay, so it turns out that so this is the crypted value. So if you want to actually send 5, okay, you will convert it into the encrypted form and send this as the output. Okay. And it's a smaller example to illustrate the same thing. So what I showed you was a direct method. So you do it one step at a time, right? And then there are some other methods. Okay, they have many methods that they have described here, right? And you can look at all these, right? And one of them is, I think it's called Montgomery method. So Montgomery multiplication and Montgomery modular exponentiation and all these are available. Okay. So let me try to uh, just a second. I don't think this is what I. Okay, maybe I can explain it to you here. I was hoping to show you the diagram, but I'm not. Okay, so see, suppose we have to multiply. Suppose we have to raise m the power some e, and e can be written in binary. So suppose e is equal to, let us say, 31 or something, not 30, say 35. So write it as a binary number. So 35 happens to be 10, then 001. I believe this is 35. Okay, this is 35. So the leftmost must be a 1. So you start by putting m and m square down. So start by putting m and m square. So you have to compute m square. And they're all modulo. Okay. So when I say m square, it is m square modulo n. Then the next bit that you see, if it is a 0, then I think 0 means I think this is 0. And so when I write like this, it means MQ. Okay, you multiply these two, and this becomes M square. So you square this. Okay, and again there is a 0. So again the same thing. So multiply these two, and you get M to the power 5, and you get M to the power 4. You are squaring this. Again 0. So same thing. M to the power 9 and M to the power 8. Now we see a 1. So now it will be like this. Okay. It will be M to the power 17 and M to the power 18. Okay. So this will be squared and this will be multiplied. And again we see a 1. So again it will be like this. So this will be M to the power 17 plus 8 is 35. And this will be M to the power 26. So notice that there are only how many multiplications did we have to do? See, we did 1 here to find M square. Then this was a square operation. This was a multiplication operation. Then this was a square operation. I think this was also a square operation. This was a multiplication. And maybe this was also a multiplication. So we have done 1, 2, 3, 4 multiplications, I think. 1, 2, 3, 4, 5, 6 multiplications. No? 1, 2. This is a multiplication. 3, 4, 5, 6. And the others are squares. If you consider squares also as multiplication, I think squaring is slightly easier than multiplication. But if you do it, so basically you are doing 1 and 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 multiplications. Okay. So if this E is a very large number, okay, its representation will have only log number of bits. Okay, even if E is very large, its representation will have logarithmic number of bits. So in each stage, we are doing maybe 2 multiplications. Right? So this will require 2 log n multiplications. Okay? So it will not require more than 2 log n multiplications. So in the case of 35, we needed 35 can be represented in actually this one is okay, 1, 2, 3, 4, 5, 6, right? 6. So we need approximately 12 multiplications according to this. So actual is I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So something like 2 log e to the base 2 minus 1 multiplications of it. So this is the, I hope you understood the algorithm. This is called the ladder. Okay, some people call it as a ladder. So I'll explain it one more with one more example so that you understand this. So I think what was the E in that other one? I don't remember. What was the E in that first example? There the E was E was 17. Okay. So E was 17 there. And D was 430. So we can try both. So we'll try E is 17 and 430. So 17 can be written as 17 can be written as 1 0 0 0 1. So we start by putting m in the end and m square. This is the initialization. So m and m square. Then you leave this first. The first one is when we just put m and m square. So then come to this 0. So 0 means you have to take this kind of a ladder. Okay. So you will multiply these two guys and you will add, you will square this guy. The next 0 means again same thing. M to the power 5 and m power. Again a 0, so m power 9 and m power 8. And once again, we finally have 1. So this way, it will be m power 17 and m power 16. So this is our answer. Okay. So in our So in our example, we had to do 65 to the power 17. So we'll write down 65 and 65 square. And 65 square will be modulo 17. I'm sorry, modulo whatever that number was. I don't remember that number now. So it was modulo 3233. So we have to calculate 65 square modulo 3233. Okay. And then go through this algorithm. At no stage you will have a number larger than 3233. Okay, because it's modulo 3233. So all the numbers will be within that range. Okay. And at the end of all these steps, you will have that m to the power. Okay. Okay. Any questions? In the same way, the other one was 400 and something, right? 400. So that you can try. Okay, it will be very similar. Okay. So give it a try. So my question to you is, how will you implement this in? Let us say you have been given a modulo multiplier. Okay, so let us assume that you have been given a modulo multiplier, right? And you have to repeatedly do this. What you have to do is a hardware for modulo exponentiation. Using modular multiplication. So think about it and tell me, and see how we can do this. Okay. So you see, it looks very, when you start, it appears very, nebulous, right? And then you have to think about it and what are the chats that are happening. I see a lot of chatting. So we can take the even bit of the register to store the multiplication. And zero comes and down. Okay, I don't know what that means. You can, this is the standard ladder network. Okay. You know what this means. N to the power 18 means I don't know what it is. Okay. So think and tell me. This is a time for you to think and develop a model for modular exponentiation using modular multiplication as a basic idea. Is this clear or you want me to explain again? Modular n is given to you like 3233. That is also given as an input. Okay. So the system will have you know E is one of the inputs, which is it may be the public key that n that we are trying to do, that is also an input. And then there is also an input which is m. This is a message. So we have to calculate m to the power e modulo n. So if you would look at the Wikipedia example, you can try the capital N happens to be 3233, right? And E happens to be 17, and M is any message. The message we cannot. It can be any ASCII character or something like that. And the same thing is required at the decryption also. See, the same hardware will work at the, this is the encryption. And see, that is the thing about any encryption. The same thing should work as decryption. So this is the message that we are sending, right? And this will go as the, this is only C. We call it as C. This guy is only C. And the C will go, and at the receiving end, this is the, let us say this message was sent, this C, actually anybody can tap, okay? Anybody can try to steal this C. That doesn't really matter because this D is private. And similarly, N also, you see this N is also public. Everybody knows. No, I'm sorry. N, yeah, N is also no. N is the same N comes here. And this will give me D to the power, D to the power, I'm sorry, other way around. C to the power D. C to the power D modulo N. Right? And it so happens that this becomes equal to M. So you will realize it is not so easy. I mean, you cannot ignore that. So when the message is transmitted, C is something that people can steal, right? And they can steal the message only if they can somehow reconstruct D. Okay. And that is very hard. So what there is a claim is that with quantum computing, they have been able to crack. See, what was the size of the, that N is the main thing. See, if it is, if they crack, RSA has been cracked before. Okay. I think in the early days, they were using maybe 128 bit or something like that, and then they doubled it and doubled it. So today they have gone all the way up to 4,000 bits. Okay. So these numbers are 4,000 bits big. So imagine multiplying these numbers, right? Multiplying two large numbers like that. Let me show you that article that I saw. So this is maybe it's somebody has said no. Okay. So it's only 22-bit they have. It's not. Okay, that is why this person is saying it's a trivially small RSA. So I think the paper claimed to do 2048 bits, which is really large. But what they are saying is, in reality, they only did 22 bits or something. All right. Though it's not such a, but there is a scale that someday they will crack such big numbers, in which case security is, no more there, right? Unless somebody finds another way to encrypt. So anybody has any ideas on how to proceed? So at least try to get a module done, no? You can say RSA encryptor. Okay. What are the inputs? You will take E and then M and maybe that N, right? And because you cannot do this combinationally, you may also require RST and clock also. And the number of bits maybe we can try to write as a parameter or something like that. To keep it some at least 64 or something like that. So your M, E and N, let us pretend they're all 64-bit numbers. The output is C. So C is also an output. What is the reset? So maybe we'll keep a we will keep two registers. See, we have to implement that ladder, right? So what is the way to do the ladder? We'll possibly keep two registers. Okay, both are, let us say, 64 bits. Okay, logic or bit n bits minus 1 to 0. Let us call them x1 and x2. Okay, so x1 and x2 are the two bits, two registers. So we can load x1 with your m, and x2 is equal to m square modulo n. So I'm assuming that this is available to me. Okay. M square is something that we already we believe that is available. So this is if it's reset. Else, what do we have to do? We have to, we have to look at that E from left to right. See, E, when I represent it as a 64-bit number, there may be a lot of zeros in the beginning. When I looked at this E here, I assumed that it was 1 followed by 0, 0, 1, but there may be a lot of zeros before. So we have to skip all of those. So all the initial zeros must be skipped. So that can also be done in the reset. Okay, we have to find the first position where it is a 1, and then we have to skip one more. Okay, so that is what we have to do. So we need some sort of a index I. So we'll go from maybe I equal to 0. Okay. While I is while E of I equals 0, we just keep incrementing I. So when this stops, I'm assuming that you will not have E equal to all zeros, etc. See, that is a fair assumption. So it will stop at some point, and no, I think we may have to start from n bits minus 1 and decrement. Okay. So we'll have to go from left to right. Okay. So we start with n bits minus 1 and keep decrementing till we find a 1. Then after that, we have to still decrement one more time. So that will be the position of the first. So skip all the And now when it is a clock, then we have to maybe look at E of I. So we may have to look at if E of I equals 0, then what should we do, right? Else, what should we do? Okay. So remember what I told you about the ladder. If I see a 0 and right, if I see a 0, I'm calling this was x1 and this is x2. If I see a 0, then I update x2 to be a product of x1 and x2, and I update x1 to this square. So we say x2 equals x1 times x2 modulo n, and x1 equals x1 times x1 modulo n. So that would update two registers. And on the other hand, if it is a 1, then it is like this. So we have to square this guy x2, and x1 will be equal to product. So x1 equals x1 times x2 times percentage n, and x2 is the or x2 equals x2. And we need to do this till I is greater than 0. Okay, we have to decrement I later. At the end of this, we have to decrement I. And we should stop when I becomes 0. If I is greater than or equal to 0, then only do this. Okay. If I is greater than or equal to 0, then do all this. Otherwise, this nothing will happen. This hardware will just keep doing it. If I becomes 0, uh, I'm sorry, if I becomes less than 1, that means we are done. Okay. So maybe we can give a signal called done or finish or something like that. Initially, we can set finish to 0. And C, which is the output, will be in, where will C be? Is it x1 or x2? The last computation, see if the last computation is a, if it's a 1, it will be in the top one, and if it is a 0, it will be in the bottom. If it is 1, x1, if it is 0, it will be in x2, right? I think that is how it is, right? Just verify. Suppose we take the case of 4, right? So 4 is 1, oops. Suppose we take the case of 4, we have 1, 0, 0. So this one means we have x1 is x1, this is x2. We have initialized it to m and m square. When we see this 0, we do this m cube and m square. And when this we do, we get m power 4 and m power 4. Suppose it is 5, and suppose it is 9 or something. Then initially x1 and x2 will have m and m square. This 0 will cause m cube and m square, m power 5 and m power 4. And we'll have m power 9 and m to the power 8. It looks like it's always going to be this. So x1 is where the answer will be. So the answer is in S1, so we can possibly assign C to X1. So that is a simple description. Okay. It's easier said than done because frankly speaking, this modulo multiplication is a challenge. And that implementation you will have to read that there is a Montgomery multiplication, which is also very similar. I mean, it's a very nice algorithm. Okay, you can try looking at that. And to test this guy, we can use RSA encryptor. Let us say RSA instance. So let us go ahead and create RST main, clock main, and let us create bits 63 to 0 of E and let's see. If you want, we can call them E main, etc. And then bit function. So here we are going to bind everything. So RST main will come here, clock main will come here, and main will come here. Then E main, then N main, C main, and finish. And initially, we can initialize E2. We'll take the example of 17, right? And N is 3233 because we know the answer from Wikipedia, right? And clock main is 0, and reset main is also 0. Then reset main equal to 1. Then reset main equal to 0. Then we'll have to send 64 pulses. When we are done, we can display ceiling. So that will be our test bench. Let us try. So if we have done it right, we should. If we have done it right, we should get. The answer I think was some 400 something. Right? It's email, right? Email. Oh, we forgot the M main. M main was 65, I think. N, something is wrong. We are getting 332. That is not the correct answer. The correct answer was 400 something, right? C is 65 to the power 17, 3 to the. This is the correct answer. 2790 is the correct answer. Wait. E is 17, 3233, right? Did I do it right? 3233. What's wrong? It will make sure that finish is all correct. So finish equal to percentage D. So according to me, that should be 1. If it is not 1, there is a problem. So finish is okay. So what could be the reason why this is not correct? We initialize x1 to m and x2 to m square. Okay. Let us display I. So I, in my opinion, should be 4, I think, right? It should be 4 if it is on correctly. Why it has become 2? Why is 2? That is a mistake, no? So we are going from I is n bits minus 1, n bits is 64. So E, so it should have been 4, 0, 1, 2, 3, 4. Unfortunately, we have already decremented once, so it has become 3. So you know what? This is wrong. See, when we stop, I think it's better to say while E of I is equal to 0, E minus minus. So this is a better thing. When I becomes 1, it will stop. At that time, I think I should have incremented. So I is 4 correct, but even now our answer is not correct. 1330 is not correct. So there is something wrong here. So if E of I is 0, if E of I is 0, we are doing, is there anything wrong here? Anybody can see? If it is 0, we do this, right? If you see a 0, this is x1 and this is x2. If you see a 0, then we are doing x1 times x2 here. And we are doing x1 square here. So if it is 1, we are doing x1 equal to x1 times x2. And this is x2 square. So just check if I have done it correctly. 0 means x1 becomes x1 square. But before that, I have to multiply x2 equals x1 times x2. Otherwise, x1 becomes x2. And then I equal to I minus 1. This should be repeated for each of the cases. 1, 0, 0, 0, 1. Okay, so it started with 4 and then 3, 2, 1, 0. So it was done 5 times. So 1, 0, 0, 0. And the answer, I believe, is in x1 is what I'm saying. I don't know. It says the answer is our answer was 13 something, no? 1330. X2 is wrong, huh? What is wrong? Oh, here it is wrong. Hmm. No, no, that was x1 square was correct, man. It was correct. This is correct. What is the error? X2 equals x1 times x2. P is x1. If E of I is 0, then do it else. I thought in both the cases it is x1, right? Let us do it. Let us display x1 and x2 here. If you think that you can display so many times. So when the clock comes the first time, I is 4, right? We display so many times. What is the answer we are supposed to get? Do you recognize any of these? We should get 2790. No, wait. That is for m equal to 65. Oh, you know what? Did I get m equal to 65 correctly? M is 65 have I given? I given. The correct answer is 2790. Fortunately, I don't see it anywhere. If we iterate one more time, it will work. Huh? Why do you say so? Because we are doing till I greater than or equal to 0, right? So we are doing greater than or equal to 0. For 0 also it will be done. So I don't think we should iterate one time. Mhm. Could it be that, say, 64-bit is a very big register? So I doubt if we are having overflow or something like. So let me do one thing, just to be on the safe side. Let me make it even bigger. Right? Okay, I'm still getting 1330. Now if I take 1330 here, then I should get back 17. Things are correctly done. Oh, sorry. This is 17. No. This is what? Is 413. 413. And this should be 1330. Then if you get back 65, then we are correct. So there is a bug. Okay. So what is the chat? Anybody seems to have some ideas. There is a chat. They should be x2. I am displaying both x2 and x1. No? Neither of them is correct. So it may be in the modular multiplication, something as well. Three two three three is correct, right? 3233 is correct. Then E is 17, and we have taken E is 17, 3233, and M was 65, I think, right? M was 65. M was 65. So 65 to the power 17 mod 3233 is 2790. So if we take 17, 3233, that's 65. Mhm. What are the other smaller example? There was a smaller example somewhere. No? I thought I saw a smaller example somewhere. Maybe in that modular. He has taken B equals 5, E equals 3, and M equal to 13. Okay, so we have to take M13. B is the message. So let us write down. What we call as M, he calls it as B, and it's 5. And what we call as E is he also calls as E. And what we call as capital N, he calls as M, and that is 8. No, 13. So let us try this exercise. Let us say E is 3, then N is 13 according to his guide, and M is 5. So let us try this. We should get 8 as the answer. See here it is correct. C is 8. So what does it show? Because the numbers are becoming too big. I don't think they can go beyond 128 bits, right? I don't see how they can do it. So you just check if there is anything wrong here. Reset clock, n bits minus 1 to 0, E, M, and N. N bits minus 1 to 0. N bits is 64. X1 and X4, in fact, y is the number. So, this is C. That is also okay. So now if you change C to 8, I don't know what E will be, right? But D, what is D here? D is 4, right? D is I doubt if Wikipedia, what is the chance that they have made a mistake? I don't think so, right? In fact, they would have verified. I don't know, guys, what is a mistake. For the smaller example, it seems to work. Is there any other example of modular exponentiation? It's taken a very small one. If somebody has given another example, it would have helped. Ah, here it is. So let us write it down. It's M is 67930 and E is 32319 and capital N is 103969. Let's try this also. M is 7, E is 1383921 and capital N is 4. So a little bit weird. Okay, let's try this. E is M is 1383921. N is 4. M is 7. Okay, let's try running this. So the answer is 3. What is the answer he gave? C is correct. We got that 3 is correct answer. We are getting correct answers for some. So I don't know what to suspect. Okay. So here also we can try. 4, let me write it down. 2, 3, 4, 9, 3, 2, 1, 2, 3, 0. Wow. What a number. And we have 4 as M and N is 15. N is 15. E is 1, 3, I'm sorry, 2, 3, 4, 9, 3, 2, 1, 2, 3, 0. This was M is to when n was 4. We are getting 1 as the answer. Okay. So here also we got the correct answer. So we are getting correct answers in many cases. Okay. So why it doesn't work for that big case? Is it because the numbers are really big and we are running out of space? That is the only thing left to try. I doubt it very much. These numbers are not that big. See, 1, 2, 3, 4. Okay, I'm not sure, guys, why we are getting this wrong answer for this. So I'll give this to you to try crack it. Okay, so I will leave this code with you guys. You can try and crack it. Okay, all right, good. So we still have a issue here, right? We have to figure this out. Okay, I will let you work on that. The other thing I wanted to give as a assignment is see another important thing in hardware is pipeline. So you may have come across pipelining in a number of situations, right? See, for example, there is let us take a trivial example of square root of if I want to find a distance between two numbers. So x1, y1 is 1 point, and x2, y2 is another point. So there are two kinds of distances. This is called as a Manhattan distance. In this case, the answer is x1 minus x2 plus y1 minus y2. The other one is the Euclidean distance. And that is x1 minus x2 whole square plus y1 minus y2 whole square. So there may be applications where you have to do this again and again, repeatedly. So we will get a sequence of x1s, y1s, etc. And we have to keep doing this x1 minus x2 plus y1 minus y2 whole square. So imagine that there are n points in the 2D space. and we have to calculate this uh, repeatedly. So you will need, unfortunately, several square operations. For each computation, we need two squares or two multiplications. We'll need one addition and one square root. Okay. So this can be, for very large values of n, this can be quite expensive. Okay. So maybe some robot may be trying to do this, right? To calculate the Euclidean distance repeatedly and things like that. So one way to organize this computation could be, so we give x1, y1, x2, y2, right? And the first stage would calculate the difference, okay, namely x1 minus x2 and y1 minus y2. So there are two, let us say, subtractors which will produce x1 minus x2 and y1 minus y2. And if we are lucky, we have two more multipliers, which will give you x1 minus x2 whole square and y1 minus y2 whole square. And then we add, then finally we have a square. These are actually floating point operations. So the hardware for floating point subtraction, floating point division, floating point subtraction, floating point multiplication. So we need all of these. And we also need a floating point square root. So if you have this much hardware, then the time it will take to do all of this will be one subtraction plus one multiplication plus one addition plus one square root. That is the time it will take to complete one operation. Okay. So we can try doing something like this. Maybe I'll show it. So the first stage, we call them as stages. So we have a stage of subtractors. Then we have a stage of multipliers. Then we have a stage of adder. Then we have square root. So what we could do is we could do something like this. So we'll bring in x1 minus y1 here and x2 minus y2 here. These two are, let us say, getting computed here. It's time step point. Then the squares of these will be computed here. And their sum will be computed here. And their square root will be computed. Now this these subtractors, see, in this time step they have nothing to do, so they can actually start computing x2 minus y2. So I shouldn't say x2 minus y2, right? This is for the next point. So maybe we should call it x1 y1 for the first point and x2 y2 for this first point. Okay. We need another index to indicate. So we let us say we have another set of points for which we are doing the subtraction, and they will be squared here, and they will be added here, and they will be square. The square root will be taken here. Okay. So it sort of keeps everybody busy after some time. So some people will write it like this. So this is for the first pair of points. Then the first pair of points will get that d1 square and d2 square. Then summation of d1 square and d2 square will happen for the first pair. And the square root will take for the first pair of points. So this is the multiplier. This is the adder. This is the square root. The second pair of points will enter here. And the third pair will enter here. And finally, the fourth pair will enter here. So you can see that at the end of this, we are getting one new computation every clock. Okay. So if you consider these as clock pulses, if you look at these as clocks, then let us say this is clock pulse 1, clock pulse 2, clock pulse 3, 4, 5, 6, 7. So once 4 enters, you can see that everybody is busy. We say the pipeline is full here. Okay. And as a result, they can all be busy. All the units are busy. So to calculate the this Euclidean distance for 4 points, we'll need 7 clock cycles. We'll need 7 clock cycles. And the period of the clock cycle will depend on the maximum of these computations. See, we have to clock it at the rate of, if this takes, let us say, T sub, if this takes T mul, if this takes T add, and this takes T square root, we have to clock it at the maximum value. So for 4 computations, we need 7 times max of that whatever I wrote earlier. In general, if it is n, see, you will need n clocks to fill the pipeline, right? And after that, you are left with the first guy will come out at the end of n 4 clock cycles. Okay, so the first guy will come out at the end of 4 clock cycles. Then we have n minus 1 more to come out. So this is the number of clock pulses required for n, okay, multiplied by t max of that. So this is the time it will take for the pipeline to complete. Whereas if we had done it sequentially, then it will take much more time. You can calculate that time. Okay, if there was no pipelining that was being done, then we'll take t sub plus t mul plus t add plus t square root multiplied by n. So if all goes well, we can get the work done 4 times as fast. Okay, so the speed up can be up to 4. So that is, see, in the industry, they like, if you can get things done twice as fast or something like that, they like that, right? It has increased the speed by 2 times, right? Or 3 times or something like that. It is coming at the cost of extra hardware. See, instead of one subtractor, you are using two, instead of one multiplier, using two, etc. So when you build something like this, right? See, there is a lot of detail, right? There is so much detail here. Imagine a complete diagram for this block, right? So there are floating point subtractors, then floating point multipliers, floating point adders, okay? And there's a considerable amount of complexity here. Mhm. And one more thing that maybe didn't get emphasized was, let us say we have the subtractors here. Then these are our multipliers. Then there is an adder. Then there is a square root. See, we are saying that as soon as this guy completes its work, right, we'll feed a new set of inputs, right? That's what we are saying. Remember, I wrote like this, right? let us say the first set of inputs were getting computed here, right? In the clock cycle 1, then others are not busy. They are still waiting for their input. Now the first guy will, the output of x1 minus x2, etc. will go x1 minus x2 and y1 minus y2 will go here. And immediately it wants to do it for the remaining guy. That second one it wants to start. Okay? So you'll have to hold the values that it has computed in the previous for the previous guys. So you will need a buffer. Because it is already beginning to work on the next pair. So it has to keep the old values, that is x1 minus x2 and y1 minus y2 in these buffers. Then it can start its work. This guy is taking the old values and doing squares, right? And it also has to keep the outputs in a buffer. Because when it starts doing the next guy, okay, then we are changing we should not start changing the outputs of these wires. Okay, so they should be safely captured somewhere, and so is the case here. So we need additional buffers to hold the intermediate value. So this is another additional overhead. So we need extra hardware. See, if you did it sequentially, you will just possibly reuse everything. See, maybe you will build a adder subtractor and you'll reuse it. Maybe you will use the multiplication again in square rooting and things like that, right? But here we are not going to do that. Everything is separate. Okay? There is a fair amount of hardware overhead plus the buffers that I talked. But it is still very attractive. So pipelining is still a very attractive thing to do. And this idea is used in a number of places. It's not just in this is just an example to illustrate, right? But it is used, in a number of places. Wherever they want, higher speed, maybe twice the speed, three times the speed, and so on, they will try to use pipelining whenever possible. So the challenge for you is to model this pipelined algorithm, okay, and show how you have, let us say there is a big queue here of points x11, x12, and so on, and y11, 2, and so on, and x21, x21, and y21, y22, and so on. So there are pairs of points, and there are many of them. There may be very large number of them. And we have to calculate the Euclidean distances, and they should be the outputs. So this is a challenge, right? And I want you to think about how to do this, right? See, it's not going to be easy if you go down to the level of, if I start building everything like floating point adders, multipliers, right? Then it becomes very complicated. So similarly, there may be so much detail here, right? So maybe it's better to use some sort of a interface or something like that, right? And talk about buses going from one module to the other, right? That may be a better way of doing that. Okay, that is sometimes we people refer to this as transaction level modeling. Where we don't get into small details, right? We say that there is a data about point one is sent to stage one, and after computation, the intermediate values are sent to stage two. Okay, so that is a very high level abstraction that would help us to model this and verify that it works correctly. And we have see, because we have to worry about how to clock these buffers. All those small details will be there. Okay, and if you say, look, I don't have these many multipliers, I will try to use the same multiplication for, I can stagger these, right? I can say this multiplier will have to do two things. Then you will realize it becomes very complicated. Okay. Suppose I say I cannot afford to have, uh, you know, two multipliers, then you can try two subtractors, then only one multiplier here, and another multiplier. The same multiplier will do the next one. Okay. So suddenly it becomes complicated. Everybody understood that? You try rewriting a architecture, right? And you'll realize that suddenly synchronization, etc., becomes quite complicated. So it's good to write a transaction level model for something like this and verify its operation, functional level operation, before we start designing all detailed multipliers, adders, and all those kind of things. Yeah. So that is a very big value addition that system Verilog or such languages provide. Okay. So system Verilog has an extension called UVM. Okay. So let me briefly show it to you. It's too complicated. It's too beyond the scope of this class. Okay. But you will find, if you are curious to know, this has certain, see, there is a TL means transaction level. Okay. There are examples on TL Verilog. There are examples on UVM here. Right. If you see UVM, I think I already copied this, so it's okay. You will find they have given, okay, some examples that you are welcome to look at. Okay. But you will realize even very simple things like, hello world, etc., you will find it fairly complicated. Okay. Just to do one simple hello world, etc., you will find that there is a great deal of coding that you will have to do and all that, right? But for bigger examples, it may be something that, but this is what the industry has adopted, this transaction level modeling using universal verification methodology, right? And they have been using, I think these are some of the simulators that they support, okay, cadence and things like that. Okay. And here, these are all various methodologies. There is also OVM was popular earlier. Okay, now I think UVM is the one which is popular. But if you are curious, please go ahead and take a look. Okay, It is beyond the scope of my class to go into these things. Okay. But if you are joining industry, they will train you in the beginning. If you are joining as a design verification engineer, you will receive some training on system Verilog followed by UVM, and you may find other training materials on UVM, etc. Feel free to look at that, but you will find that it's very detailed. Okay, so a lot of basically it's reusing a lot of libraries that are already there. Okay, so you will have to get used to that kind of a thing. Okay, so I will not go into more of UVM. Like I said, there are many others. See TL Verilog. That's another sort of language. It's called transaction level Verilog. Okay, so there are some examples here of I think Conway's Live or something like that. You can see it's also not. This they claim is easier than Verilog, etc. But you'll have to get used to it. Okay. So this is a very they claim that this is a much less code than say there is a small game called Conway's Game of Life. Okay. So read about it, right? And you will understand how UVM will support in things like the functional coverage. Okay. So, see in that example of the let's go back to this example. So when we start giving random, let us say, inputs to this, have we done enough functional coverage? Okay. Have we verified it sufficiently, and does this algorithm work? Does our architecture, correctly work? This example, you may think what is so difficult here, right? But imagine it's an instruction pipeline. Okay. So there may be a fetch stage, there is a decode stage, and then there is execute stage, right? And then there could be things like, how are you handling jump instructions in the pipeline, right? And then there is, sometimes what can happen is when you are in a pipeline mode of operation, there may be dependency between one instruction and the previous instruction. So as a result, you may have to once again go back and restart. Okay, if there is a dependency between two instructions, then you may not be able to do it correctly, right? Pipelining will not be correct, right? So in that case, again, you will have to restart the pipeline. So there are many such, complexities that come up when you implement things like instruction pipelines. Uh, or let us say we have what are called as say I mentioned to you that I don't have enough multipliers, so I may want to use the same multiplier for doing both these, or I may use the same multiplier for doing one of these square root operations also. So scheduling becomes quite difficult. The pipeline scheduling becomes such a thing is called as a non-linear pipeline. So this is all nice and linear. Data only flows in one direction. But in a non-linear pipeline, data may have to go back also. So we, after computing this multiplication, we may have to send it back for some addition and things like that. So suddenly it becomes more complicated, right? So verifying such a thing to make and seeing that all the computations work correctly is not a trivial task. Okay, so that is where this transaction level modeling and UVM and TL Verilog, etc. are being used. Okay, I think among all the things that you saw there, TL Verilog and so on, I think UVM has been quite well accepted in the industry. So feel free to look at the exercises and see if any of them appeal to you. So it will help you in making a career decision. See if you are really considering the career of a design verification engineer. It's a good idea to go through what kind of things are done there. Okay, so that you can better appreciate. Okay. All right. Any questions? Try to debug that code. I will send that code to Professor Vinay and he will share it with you. So see if you can spot. I'm not able to see. It seems to work for many small examples. So I'll have to fix and I'll have to see, and you can also see what exactly is going on. Okay. So we'll meet tomorrow. And no, Agile, Matthew, I cannot do that. Okay, that is out. I told you it's out of the scope. So you can read it yourself. Okay, it is not. Nobody teaches UVM at the university level. Okay, that is not the right thing to do. All right, I will see you tomorrow.